There's a photograph that changed astronomy on June 25th, 2025. It does not look like much at first glance. A field of deep black, a smeared blue glow in the center where a star used to be, deliberately erased from the image by one of the most precise optical systems ever built and launched into space. And then, in the upper right corner of the frame, a single small dot of orange, faint, quiet, almost easy to miss. That orange dot is a planet. Not a planet in our solar system. Not a moon of Jupiter or a distant dwarf world beyond Neptune. That orange dot is a world orbiting another star, 111 light years from Earth, captured in direct infrared light by the James Webb Space Telescope for the first time in the history of astronomy. Its name is TWA 7b. It has a mass roughly equal to Saturn. It is approximately 47 degrees Celsius. On its surface, warmer than a hot summer day on Earth, for a world that orbits its star at 50 times the distance Earth orbits the Sun. It is approximately 6 million years old, a newborn by cosmic standards, still glowing with the residual heat of its own formation. And when the lead scientist on the discovery team, Dr. Anne-Marie Lagrange of France's National Center for Scientific Research, looked at the final processed image and saw that orange dot confirmed in the data, she said something that every scientist in her position probably would have said: "We are really witnessing the youth of a planetary system." The James Webb Space Telescope E had just done something that no space observatory before it had managed to achieve. It had found a planet by actually seeing it, and the scientific world has not been the same since. To understand why this discovery matters so profoundly, you need to understand how almost every other exoplanet in history has been found, and why the method that found them, while extraordinarily powerful, has a fundamental limitation that direct imaging does not share. The modern era of exoplanet discovery began in 1995, when astronomers Michel Mayor and Didier Queloz detected 51 Pegasi b, a hot Jupiter orbiting a sun-like star, using a technique called radial velocity, also known as Doppler spectroscopy. The basic principle of radial velocity is that a planet, as it orbits a star, does not simply circle a stationary object. The planet and star orbit their shared center of mass together. If the planet is massive enough, it pulls the star in a tiny cyclical wobble synchronized with the planet's orbit L period. As the star wobbles toward Earth, its light is compressed slightly, shifted toward blue. As it wobbles away, its light is stretched slightly, shifted toward red. By measuring these Doppler shifts in the star's spectral lines with extreme precision, astronomers can infer the presence of a planet, its minimum mass, and its orbital period without ever seeing the planet itself. The planet is never directly observed. It is detected by the motion it induces in a star that astronomers can see. The transit method, which became even more powerful when the Kepler Space Telescope launched in 2009, works on a similarly indirect T principle. When a planet passes in front of its host star from the perspective of Earth, a transit, it blocks a tiny fraction of the star's light. For an Earth-sized planet transiting a Sun-sized star, the dimming is approximately 0.01%, 1 part in 10,000. For a larger Jupiter-sized planet, the dimming reaches about 1%. By staring at fields of thousands of stars simultaneously and watching for these periodic, precise dimmings repeated over multiple orbital periods, Kepler and its successor TESS identified thousands of exoplanet candidates. Combined with the radial velocity follow-up measurements that confirm most of them, the transit method has produced the vast majority of the nearly 6,000 confirmed exoplanets in the NASA Exoplanet Archive as of June 2025. Every one of those planets was found by watching what it did to its star's light, the shadow it cast, the wobble it induced, not by seeing the planet itself. This distinction between inferring a planet's existence from its effects on a star versus actually photographing the planet's own light is not just a technical difference, it is a difference in what you can learn. When you detect a planet through the transit method, you know its orbital period, its size relative to its star, and if you're lucky and the atmosphere transmits measurable amounts of starlight through it, you can analyze the spectral fingerprints of the gases in that atmosphere. Transit spectroscopy has revealed water vapor, carbon dioxide, methane, and other molecules in the atmospheres of dozens of exoplanets. But transit spectroscopy mixes the planet's atmosphere signal with the much brighter light of the star, requiring enormous precision and multiple transits to extract meaningful data. And transits only occur for planets whose orbits are aligned to pass in front of their star from our specific vantage point. The vast majority of planets in any given star system are not aligned this way, and are therefore invisible to the transit method entirely. The radial velocity method finds planets through wobble, which means it is most sensitive to massive planets orbiting close to their stars, Jupiter-mass worlds in tight orbits that pull their stars hard. Small planets, far from their stars, in orbits that would be considered habitable zone candidates are nearly impossible to detect by wobble alone because their gravitational tug on the star is too small to measure at stellar distances. Direct imaging bypasses all of these constraints. When you photograph a planet directly, when you capture photons that originated from the planet's own surface or atmosphere, not from the star it orbits, you are measuring the planet itself. You can measure its temperature from its infrared brightness. You can take its spectrum and identify the molecules in its atmosphere without the overwhelming contamination of stellar light. You can track its motion over multiple observations and determine its orbi, T directly, without relying on the periodic signatures that transit and radial velocity depend on. And most importantly, you can find planets that would be completely invisible to every other detection method, planets that do not transit from our perspective, planets too small and too distant from their stars to produce measurable wobbles, planets that exist in orbital configurations that indirect methods simply cannot reach. The reason direct imaging is not already the dominant planet-finding technique is that it is fantastically difficult. A planet orbiting a star is like trying to photograph a firefly sitting next to a lighthouse from a distance of several miles in the dark. The star is not just brighter than the planet, it is millions or billions of times brighter, depending on the wavelength of light you're observing and the type of planet involved. The planet's signal is completely overwhelmed by the star's glare at the angular separations that correspond to planetary orbits around distant stars. The star that TWA-7b orbits, designated TWA-7, also known in older catalogs as CE Antillae, is a young low-mass star in the TW Hydrae Association, a loose grouping of young stars that formed from the same molecular cloud approximately 5 to 10 million years ago. The TW Hydrae Association is one of the closest regions of recent star formation to Earth, making it a natural target for astronomers studying how young planetary systems form and evolve. TWA-7 itself is classified as an M-type star, a red dwarf, smaller and cooler than our Sun, with a mass approximately 55% of the Sun's. It is surrounded by a debris disk, a flattened ring of dust and rocky material left over from planet formation, glowing in infrared light because the disk particles absorb radiation from the central star and re-emit it as heat. Debris disks are the solar system analogs of the asteroid belt and Kuiper belt, the remnants of a planet formation process that swept up most of the primordial material while leaving a residue of smaller bodies and dust behind. The disk around TWA-7 had been studied extensively before the JWST observations. Observations by ESOs vary. Large telescope using the SPHERE instrument had revealed that the disk is not a simple uniform ring. It has structure, including at least 3 distinct ring-like concentrations and, critically, a gap, an empty region within the disk where the dust density is dramatically lower than surrounding areas. Gaps in debris disks are not random. They are sculpted by planets. A planet embedded in or near a debris disk gravitationally captures and ejects the dust and small bodies in its orbital zone, clearing a path through the disk that is visible as a low-density gap in imaging. The gap in TWA-7's disk was the first clue that something was there, a theoretical planet that the disk structure implied, but that no instrument had been able to directly detect. The observation that changed everything was performed on June 21, 2024, using JWST's mid-infrared instrument called MIRI, equipped with a specialized coronagraph developed by a consortium led by the French National Centre for Scientific Research in collaboration with the Centre for Extragalactic Astronomy at Durham University in England. A coronagraph works by physically blocking the light from the central star, creating an artificial eclipse inside the telescope before that light reaches the detector. The concept mimics what happens during a natural total solar eclipse, when the moon's disk blocks the sun's photosphere and allows the sun's faint corona to become visible. In a space telescope coronagraph, a precisely shaped opaque mask covers the star's image at the focal plane of the instrument, preventing that light from continuing through the optical train to the detector. What remains after the mask is applied is the light from everything surrounding the star, the debris disk, background stars, and any planets that happen to be present. The MIRI coronagraph used for the TWA-7 observations uses a technology called a 4-quadrant phase mask, a coronagraph design that divides the focal plane into 4 quadrants, introducing phase shifts that cause the starlight to destructively interfere with itself, while allowing off-axis light from surrounding objects to pass through relatively unaffected. Even with the coronagraph in place, residual starlight leaks through the mask and creates a bright speckle pattern on the detector, a noise floor that faint planets can easily be buried in. The research team, led by Dr. Lagrange, applied advanced image processing algorithms to subtract this ReZAD UAL starlight pattern, Using multiple exposures taken at different orientations to separate de manière style, he fixed speckle pattern of the telescope and instrument from any real astrophysical sources that would rotate consistently with the sky as the telescope's orientation changed. When the residual starlight was subtracted, a faint infrared source remained. It was sitting approximately 1.5 arc seconds from the star, a tiny angle, but one that corresponds at the distance of TWA7 to approximately 50 astronomical units, 50 times the distance from Earth to the Sun. That is well outside the orbit of Neptune in our solar system, in the region where comets dwell. And it is exactly where the gap in TWA7's debris disk had suggested a planet should be. The confirmation that the detected source was actually a planet, rather than a background star or some artifact of the imaging process, required multiple lines of evidence. First, the team checked whether the source was consistent in brightness and position with being a background object. A background star at the distance of TWA7, 111 light-years, would appear at a fixed position on the sky, while TWA7 itself moves along its proper motion path. By comparing the JWST observation with earlier very large telescope data from different epochs, the team confirmed that the detected source was moving together with TWA7. It shared the star's proper motion, proving that it is physically associated with the star and not a coincidental background object. Second, the brightness of the source in MIRI's mid-infrared bandpass was compared against atmospheric models for young, cold planets of various masses. The observed infrared luminosity of the source was consistent with a planet of approximately 0.3 Jupiter masses, roughly 100 Earth masses, at a temperature of approximately 320 Kelvin, which translates to about 47 degrees Celsius. That temperature is warmer than you might expect for a planet at 50 astronomical units from a dim red dwarf star. But it is consistent with a planet that is only 6 million years old, still radiating the heat of gravitational contraction, the same process that made Jupiter glow in its early history. Third, the location of the detected source was compared against simulations of what planet is needed to produce the observed gap structure in TWA7's debris disk. When the team ran dynamical simulations, placing a planet at the detected position with the estimated mass, the resulting disk structure, including the gap, the inner ring boundaries, and the outer ring morphology, matched the observed sphere data with remarkable fidelity. The planet was not just detected in the image, it was predicted by the disk structure, and the image confirmed exactly what the disk structure had implied. Dr. Lagrange, speaking in the ESA press release accompanying the Nature paper, stated that TWA7b is the first exoplanet light enough to be directly photographed, and that this result marks a new chapter in the direct imaging of exoplanets. Co-author Mathilde Malin from Johns Hopkins University and the Space Telescope Science Institute described the discovery as an exciting step forward in understanding planetary systems, including our own. And from the perspective of what future observatories will be able to do with this demonstrated capability, postdoctoral researcher Aaron Carter of the University of California, Santa Cruz, who has been involved in JWST's broader exoplanet direct imaging program, noted that we have only just begun, and that there are many more images of exoplanets to come that will shape our understanding of their physics, chemistry, and formation. What TWA7b's discovery immediately changes is the observable mass range of planets accessible to direct imaging. Before June 25th, 2025, the minimum mass planet any telescope, space-based or ground-based, had ever directly imaged was approximately 2 Jupiter masses. The detection of TWA7b at 0.3 Jupiter masses moves that minimum threshold by a factor of more than 6. And crucially, the Nature paper's analysis showed that the MIRI coronagraph used for this observation could have detected planets as light as 25 to 30 Earth masses, roughly the mass of Neptune, at the same orbital distance from the star. That is not a theoretical extrapolation. It is a detection limit derived from the actual noise floor of the observation. JWST is not just capable of finding Saturn-mass planets at other stars. It is potentially capable of finding Neptune-mass planets. And the paper's authors are explicit that this capability opens a new window in the study of sub-Jupiter-mass planets using direct imaging. Neptune-mass worlds around other stars are extraordinarily difficult to find with any other technique at orbital distances corresponding to the outer solar system. The gap that TW7b occupies in the parameter space of detectable planets, cold, light, young, widely separated from its star, was previously invisible to science. JWST has made it visible. The broader context for this discovery includes several parallel tracks of JWST direct imaging science that were already underway when the TWA7b paper was published. NASA's Jet Propulsion Laboratory had announced in September 2022 just months after JWST began science operations, that a directly imaged exoplanet, HIP 65426b, a much more massive gas giant between 6 and 12 Jupiter masses, located approximately 385 light-years from Earth. That 2022 observation was a demonstration of JWST's coronagraphic capability using an already known planet as a test target, confirming that the hardware performed as designed. TWA-7b is categorically different. It is the first time JWST has discovered a previously unknown planet through direct imaging, finding something that no prior observation had detected. JWST has also been using its coronagraph to study the 4-planet system around HR 8799, imaging all 4 planets in the mid-infrared and detecting for the first time the warm inner dust belt between the innermost planet and the central star, revealing structure in that system that had been predicted but never observed. And in May 2026, JWST made headlines again when it directly studied the surface of a rocky exoplanet for the first time, with researchers describing a dark, hot, barren rock based on thermal emission measurements, a completely different capability from direct imaging, but one that demonstrates the telescope's versatility across every mode of exoplanet investigation. The road from TWA-7b to the kind of direct imaging that most people imagine when they think about photographing another planet. A clear, detailed image of an Earth-like world showing surface features, atmospheric colors, oceans perhaps, or at minimum a spectral fingerprint of oxygen and water vapor in the atmosphere of a planet in the habitable zone of a sun-like star, is still a long one. The problem of photographing an Earth twin around a nearby star is orders of magnitude harder than photographing TWA-7b. A planet the size of Earth in the habitable zone of a sun-like star orbits at 1 astronomical unit, far closer to the star than TWA-7b's 50 astronomical unit separation, meaning the angular distance between planet and star on the sky is far smaller, and the challenge of distinguishing the planet from residual starlight is far more severe. Earth reflects visible sunlight rather than emitting infrared light from its own heat, making it billions of times fainter relative to its star than a young hot planet like TWA-7b, rather than millions of times. And detecting the biosignatures that would indicate life, oxygen in combination with methane, for instance, a chemical combination that is out of equilibrium in a way that biology maintains but chemistry alone cannot, requires spectroscopy of a planet signal that would be buried in noise levels that even JWST cannot overcome. Dr. Lagrange acknowledged this explicitly, noting that directly capturing images of faraway worlds similar to Earth will require even more telescopic power, the kind that the extremely large telescope, currently under construction in the Atacama Desert of Chile and expected to see first light in 2028, is specifically designed to provide, with a 39-meter primary mirror that will give it the angular resolution and light-collecting power to attempt exactly this kind of observation for the nearest stars. But the discovery of TWA-7b is not a consolation prize on the road to Earth imaging. It is a fundamental scientific result in its own right, and it has already changed what planetary scientists know about how young planetary systems are structured. TWA-7b exists inside the debris disk of a 6-million-year-old star, which means it formed within the first 6 million years of the star's existence. Planet formation timescales are one of the most actively debated questions in planetary science, and finding a Saturn-mass planet fully formed in a 6-million-year-old system provides a constraint on those timescales that models of planetary formation must account for. The planet is also sitting at 50 astronomical units from a red dwarf star, a region so cold and distant that the classical core accretion model of planet formation, in which planets grow by accumulating gas and solid material from the protoplanetary disk, struggles to explain how enough material could accumulate at that distance to form a Saturn-mass body in 6 million years. An alternative formation mechanism called disk instability, in which a gravitationally unstable region of the protoplanetary disk collapses directly into a planet-mass body without the slow core accretion process, is more easily reconciled with the existence of a cold, distant Saturn-mass planet at this early age. TWA-7b does not prove that disk instability formed it, but its very existence at this location and this age is a data point that the community will be working into planet formation models for years. What has changed, as of June 25, 2025, is the fundamental fact of what the James Webb Space Telescope can do. For 3 years after its first science observations began in July 2022, JWST revolutionized astronomy in every direction it pointed, peering back to galaxies formed within 300 million years of the Big Bang, discovering complex organic molecules in the atmospheres of exoplanets, resolving star formation regions inside our own Milky Way at resolutions never previously achieved, and revealing the atmospheric chemistry of transiting worlds with a precision that every earlier observatory could not approach. But every exoplanet it studied was one that another telescope had found first. JWST-YS, the most powerful characterization tool ever built, but it had not yet, in its first 3 years, found a new planet on its own terms by seeing it. TWA 7b ended that, the orange dot. In the upper right corner of the MIRI image is not just a planet, it is proof that the James Webb Space Telescope is not only the deepest eye humanity has ever turned on the cosmos, it is a planet finder. And now that it has found one, the question that every exoplanet astronomer on Earth is sitting with is the same question that comes after every breakthrough discovery in the history of science. What else is out there, waiting in the dark, that we have not yet seen? The telescope is pointed, the coronagraph is ready, and the answer, in orange infrared light, is coming.